Okay, hi there. We are going to go through a couple of exam questions on variable acceleration. I strongly recommend reviewing the chapter of variable acceleration and watching the video that I have made on variable acceleration. This is an exam question to test your skills to see that you can bring several ideas from the chapter together. And let's get to it. So let's read the question carefully and make sure we've got the correct understanding going through this question. The question reads as follows. A particle P moves along the x-axis. At time t seconds, the displacement of P from the origin in the positive direction is x, where x is that formula, 4/3t cubed minus 3t squared minus 4t. Find the value of t when P is instantaneously at rest. Okay, so for those of you who've seen my video, I had a flowchart between displacement, velocity, and acceleration. And you would have seen that if you're given displacement in the question like here, and you need to find velocity, you need to differentiate. Okay, displacement is at the top of the chart, and velocity is one level down, so you need to differentiate. Now, why are we talking about finding velocity? Well, let's read the question. Find the value of t when P is instantaneously at rest. I mentioned in the previous video that the term instantaneously at rest comes up very, very often in mechanics exam questions at A level. And the term instantaneously at rest, which means momentarily not moving at that split second, means if it's not moving, we have to solve when the velocity is zero, i.e. it's not moving. But we need to have the velocity. We don't have the velocity. So we're given the displacement and we need to differentiate to get the velocity, and then we need to set that to zero. That's the understanding. That's what we have to do for part A. So let's do that. Okay. So we're given the displacement. And like I mentioned, the velocity is dx by dt. It is the derivative. Differentiate the displacement equation given to you and you'll get the velocity. This equation here, so that's simple differentiation. This equation here is the general formula for velocity. So that's the velocity formula for all possible times. What do we want to do with the velocity? We could work out a specific velocity, but that's not what the question asks us to do. The question asks us to find when it's instantaneously at rest. So let's set that equation equal to zero, because that's what instantaneously at rest means. Notice I've divided the equation by 2, which you can only do once you've set it to zero. I can't just divide the velocity by 2 because I fancy it. It's only when you make it equal to 0, you then have the option to divide by 2. You don't necessarily need to do that. And then you solve that quadratic. The quadratic does factorize. Of course, on the new A-level calculators, you can then solve that directly from the calculator, which you may decide to do because it's easier. And you get 2 values. Notice I've crossed out the -1/2 value. It's probably worth writing both values in and showing the examiner that you understand that t equals -1/2 doesn't apply. Why? Because t represents time. Time is negative. In fact, it spells it out in black and white in the question. It actually tells you that t has to be bigger than or equal to 0. But in the context of a question that involves time, that should be obvious. There's no such thing as negative time. But it's worth writing both t values, then crossing out the value that is nonsense in this case, leaving you with the one value, which is t is 2. Notice the question does say find the value of t in the singular. So I was only supposed to get one value anyway. That's part A. Part B, find the acceleration of P when t is 3. So if you go back to the flowchart in my previous video, you would have seen that S is at the top, or X. Sometimes use X for displacement like they do in this question. If you go down one level, you differentiate, you get velocity. And if you go down another level, and you differentiate, you get acceleration. Because I now have found the velocity in part A, there's no point going back to the displacement and then differentiating twice. You just take your general velocity found in part A and you differentiate it. So A is the differentiation of the velocity, which we found in part A, which was 4t squared minus 6t minus 4. That simply differentiates to 8t minus 6. That's the general acceleration. And then pause, take a step back. What do I want to do with the acceleration? Well, I want the acceleration at a specific time value. So all I do now is substitute t equals 3 into here. 8 times 3 is 24, minus 6, which is 24 minus 6, which is 18. Give it a unit, meters per second squared. So quite a high acceleration when t is 3. And that's part B. Now, the part C, which is a distance traveled question. Again, in my previous video, I made a big point that in the exam, they love testing distance traveled questions. We have to be careful because distance is not the same as displacement. So when you are working out the distance traveled, you have to be careful because you must not work out the displacement. The displacement and the distance is not necessarily the same thing. So I mentioned in a previous video, you can look at that for a detailed understanding and explanation of it, that you must check if the velocity is 0 in the interval between 0 and 3. Now, like in this question and in other exam questions as well, they've been quite kind to us in that they have asked us to find when the particle is at rest. So actually we didn't realize that in part A, they weren't just asking to find the value of t when p is instantaneously at rest just because they fancied it. That's actually going to help us for part C. Had they not asked us to work out when it was at rest, you would have then had to go away and work out when it's at rest. I explained that in my variable acceleration video. Now, so let's see. The only time we care about when it's instantaneously at rest if there is a t value in between 0 and 3 when it's at rest. There might not be. Okay, so if you recall the value, it was only one value. The value that we found, okay, was t equals 2. Now that's going to interrupt me, isn't it? T equals 2 lies in my interval between 0 and 3. If it was rest when t was 5 or 7 or 20, I wouldn't care, right? It doesn't concern me. But t is 2 does. And when we work out the distance traveled, like I've got up here, it is the integral of velocity between 0 and 3, but you're going to have to split up the integral if there's a value in between when it's at rest. So I cannot integrate from 0 to 3. I have to integrate from 0 to 2 and then from 2 to 3 separately. Now, except in this question here, we don't need to do any integration whatsoever, because if you integrate velocity, and by all means, if you wish to integrate velocity, the velocity you would have found in part A, all you're going to get is this here. And for those of you, maybe, if you tried this question, okay, that's what you did. So integrating velocity just gives you the formula for x, okay, which is actually given to you in the question. And there might be another question where they start off by giving you the velocity, so you wouldn't have had that. So in this case here, you can go straight to the square brackets. Okay, like I say, if you had integrated the velocity you found, all you would have got is this, but you would have wasted a little bit of time because that's effectively given to you in the exam question. Like we said already, we need to split it up. We need to split it up between 0 and 2, and then between 2 and 3. And you have to do those integrals separately because one of them will be negative. Now, I mentioned also in the previous video, that the reason for splitting up is one of those the result will be negative, and you'll have to remove the negative to work out the overall distance traveled. You would have lost that had you done it in one go, and unfortunately you would have got the incorrect answer. Right, this is just some number work, it's not very hard. Let's put 2 into there, there, and there, and you subtract putting 0 into there, there. It's quite nice because when you put 0 into all these terms, you don't get anything, so it's effectively the left square bracket is just found by inputting the value 2. So let's do that. And you get minus 28. There we are. So the left-hand integral, which we did straight away, gives us a negative result. So when we finish, we're going to have to remove that negative okay, because that represents an area under the graph. It's just displacement in the opposite direction, and we were going to remove that negative. Right, then we go on to the right-hand square bracket, so you put 3 into here, 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 2 into there, there, there. Carefully show you're working. Input the 3, input the 2, subtract the 2 values. Okay, carefully using your calculator if you use your calculator for this part. So if you put 3 into that expression, you'll get -3. You then subtract when you put 2 in, but when you put 2 in, as we know, you get -28/3 from the left, and that gives you 19/3. Then any negative results, you need to strip away the negative. So it's 28/3 plus 19/3 is 47/3. It's a distance, so give it a unit, it's meters. It's usually meters, but just check in the question. And that is okay. If this is the second question, please pause the video if you have not had a go at this question. Have a go at it, and then come back. Right, so in this question here, you are given the velocity function. That's the general velocity in terms of time. Let's read the question carefully. It's leaving the origin O. So if you imagine the origin on an XY plane, that's where it starts, and it's moving in a straight line along the x-axis, moving in the positive x direction. Now we're told here the particle is instantaneously at rest when t is t1 and t is t2. Again, this term instantaneous at rest comes up time and time again in exam questions. And we've established with the last question and also in my previous video that the velocity is 0 when it's at rest. So all we have to do is solve the velocity as 0. Now in some exam questions, to solve v equals 0 requires us to differentiate or to integrate to get the velocity in the first place. But actually we've got the velocity here, right? We're given the velocity. So all I need to do is set that velocity to 0 and solve it straight away. It's quite nice. It's almost on a plate for us. So for part A, 3t squared minus 16t plus 21, set that to 0. You end up having to solve a quadratic equation. You can then use your calculators to solve that, or factorize, and you'll get 2 values, 7/3 and 3. Right, here's a little bit of exam technique for you. The exam question here specifies that it's at rest at 2 points, T1 and T2. They've called it 2 special things, which they don't always do. And they've specifically labeled that T1 is less than T2. So the smaller one is T1, and the bigger one is T2. Out of 7/3 and 3, hopefully we can realize 7/3 is smaller than 3. So T1 must be 7/3 and T2 must be 3. You must label T1 and T2 correctly. Right, let's move on to part B. Part B says, find the magnitude of the acceleration. This is not too difficult. Again, referring to your flowchart, the acceleration is found by differentiating velocity. Acceleration is the rate of change of velocity. So all we have to do is differentiate the velocity that's given to us in the exam question, but it doesn't say just to find the generic acceleration. It wants specifically when t is t1, and we've established t1 is 7/3. So let's differentiate the velocity to get the general acceleration, and let's substitute in 7/3. So let's do that. Okay, on to part B. Part B wants the acceleration. We know from our diagram the acceleration is at the bottom of the chart. Found by differentiating the velocity. Acceleration is the rate of change of velocity. We are given the velocity in the question, as we used in part A. So we'll have to differentiate that to get the generic acceleration. But then it wants us to actually find the acceleration at a specific time value, which we found in part A. T1 we found was 7/3. Let's put that in. Okay, so 6t minus 16. Input 7/3 into that. You get 6 times 7/3, which is 14. Minus 16 gives you -2 meters per second squared. Now, where a lot of students might slip up is the fact that the question asks us the magnitude of the acceleration. So effectively we've got a deceleration here, but it asks the magnitude. The magnitude of the acceleration is the size of the acceleration, okay, not the direction. If it said find the acceleration, that would have been our answer, -2 meters per second squared. So it shows you have to be very careful to read every single word in an exam question. The magnitude means the size. So we're not concerned that the minus is in the opposite, is there. The minus just tells me that the acceleration is in the opposite direction, causing me to decelerate. If the acceleration acts in the opposite direction to which I'm moving, then effectively there's a deceleration. This means that my final answer is 2 meters per second squared. The magnitude is the actual value. The minus just tells me the direction. So if they ask for the magnitude, they just want to know the value. Okay? The fact it's in the opposite direction, which means it's effectively a deceleration, is irrelevant. We just want the size. So you need to actually state that to get that final mark in part B. It's quite a subtle point. Right. Part C. Another distance traveled type question. Like in the previous question, like I mentioned before, a distance traveled question, you need to be very careful to establish if there is a t value in between t1 and t2, which we now know is 7/3 and 3. If there's a t value in between there where it's at rest, because when it's at rest, it turns around and you have to split up the integral needed for the distance travelled. However, we found when it was at rest in part A, t1 and t2. Those were the only values when it was at rest. And we want the distance travelled between those two t values. So there's no t values in between that's going to cause us any problems. So it means I can do the distance travelled in one straight integral. I don't have to split it up because it's at rest here, it's at rest here, but there's no values in between where it's at rest, because that's just the nature of this question. So if I want the distance travelled between t1 and t2, I just need to integrate the velocity between t1 and t2, and I just need to check. If the final answer is negative, it means the whole area is under the graph. I might have to get rid of that negative. If we're lucky, the whole result is positive, and then that's the answer. So it's quite nice. We don't have to split up the integral here. So here we go. We can do the integral in one go. 7/3 to 3. We integrate the velocity. That's how you work out distance travelled. It's just a question whether you need to split up the integral, but in this case we don't. If you integrate that, you get t cubed minus 8t squared from that, plus 21t. Input 3 into there, there, and there. Then input 7/3 into there, there, and there, and subtract. Let's see what we get. If you put 3 in, you get 18. If you put 7/3 in, you get 490/27. If you subtract, you get minus 0.148. That's a value to 3 significant figures. And you get minus 4/27, leaving it as a fraction. This means that the distance travelled is completely in the reverse direction in the range between t1 and t2. So remember, distance is not a vector, displacement is a vector, which means that the answer, just like you'd have to do if you had to split up an integral, any integral found that is negative, you have to get rid of the negative. So this time we did it in one go, but we still have to get rid of the negative. All this means is that the total distance travelled between t1 and t2 is in the opposite direction of the way I was moving, and therefore the final answer is 4/27, or 0.148 without the negative. And that is the final answer for that. Right, part D. Perhaps this is the trickiest part of the question because it's not so obvious what the question's really requiring you to do. So let's read this question and actually pick it apart. Show that P does not return to the origin. Where have we read about the origin? Up here. A particle P leaves the origin. So the origin is where we start. If it's where we start, okay, it's before we've gone anywhere. In other words, it's when S is 0. Yeah, makes sense. Okay, if it leaves the origin, that's where we're starting. That's before we've covered any ground whatsoever. If the p does not return to O, that means there's no possible t value after the beginning, i.e. after t equals 0, that we get back to where we started. Remember, if you go back to where you started, s is 0. So that means that the only possible value I can have for s is equal to 0 must be the beginning, t equals 0. I know that because it tells me in black and white that the particle leaves the origin at the beginning. So therefore, it must, before you start, obviously you're at s equals 0, but you won't necessarily return to your start point in a given journey. You might do, but apparently in this particular example, you don't. So we have to prove that the only t value for s is 0 is 0 right at the beginning. So how do we do that? Really, you need to consider the reverse case. Okay, let's try and see when it is at the origin, okay, when it possibly would return to 0. So if you investigate when s is 0, when am I at the start point effectively? Okay, when have I not moved from the start point? So if you solve the displacement equal to 0, notice we've got the displacement now. The displacement was the answer to this integral here. This is an expression for displacement. Okay, so if you set that equal to 0, that's quite nice. There's no number term there, so you can take t out as a factor. And now we can reference this back to the question. We're supposed to prove that p does not return to 0. In other words, after t equals 0, it never comes back to s equal to 0. So I can clearly see from the t at the beginning that t is a solution. T equals 0 is a solution. That t represents t equals 0. Okay, and then this bracket, if you set that to 0, well, we're not supposed to get any results. Now, where have we learned before in the course for a quadratic not to produce any real values? The discriminant. Okay, so if you just work out the discriminant of this quadratic, you'll find it's negative, which means that this bracket doesn't produce any solutions. So the only solution is the t in the front. So if you set t equal to 0, that's the only solution. There's no solutions from there. So let's see that. There we go. This bit here, t equal to 0. This bracket here, if you work out the discriminant, you have minus 8 all squared, which is 64, minus 4 times 21, which is 84. So 64 minus 84 is minus 20. So we get a negative discriminant, and therefore just give a wordy conclusion. Therefore, the only solution to s is 0 is t is 0, which has answered the question. We had to prove it did not return to 0, and we've now proven that. We've proven that because the only solution s is right at the beginning, i.e. there's no other value after t equals 0 where it's at the origin, and therefore it does not return to 0.